Welcome to Sector for Research Methods. We'll be talking today about factorial designs. We'll over some terminology, talk about interpreting the results from factorial studies, look at graphing the results and interpreting those graphs for such studies, and then talk about the utility or the uses of factorial designs. Okay, in terminology. We're talking about factorial designs. What's a factor? Well, a factor is simply a grouping variable, a variable used in a study to assign people to different groups. Now, in an experiment, your grouping variable is going to be your independent variable. But your factor or grouping variable doesn't have to be an IV. It could also be a quasi-independent variable, so a variable you don't manipulate. If you're looking at differences between people on some variable where group membership already exists, people who are first year, second year, and third year students, are the differences among those groups? Well, you didn't assign them to that level, so it's not a true independent variable. It'd be a quasi-independent variable if you think there's sort of cause and effect there. And you might also see the term subject variable. So just looking at differences in people based on some characteristic about themselves that, again, you didn't manipulate, you didn't assign. Ethnic differences, age differences, if you make age categorical. Those would be examples of subject variables that could be factors, right? So any way that you can kind of put people into groups to say, okay, this group versus that group, that way that people differ would be a factor. Now, in factorial designs, your factors can be a between subjects factor or a within subjects factor. In a between subjects factor, people only receive one level of the factor, right? So if, okay, you're in this group or this group, you're in one or the other, group A, group B, or group C. And so we're looking at differences between these people depending on which level of a factor they belong to, experience, and so forth. A within subjects factor, somebody experiences or belongs to all levels of a factor, right? So if we're doing our kind of simple drug study, 0 milligrams versus 10 milligrams versus 20 milligrams, and know that if it's a within subjects factor, if drug is a within subjects factor, you're going to get all levels, right? We'll give you no drug and then measure the dependent variable, see what happens to you. Wait a while. Okay, we'll give you 10 milligrams, measure the DV to see what happens to you. Wait a while for the effects of the drug to wear off, and then we'll give you 20 milligrams and measure the DV again to see what happens to you. Right, so, and any of your factors can be either between or within subjects factors. As I've already alluded to, every factor has a certain number of levels, right? And that's just differences in the factor. So what's the minimum number of levels a factor has to have to be a factor? Well, you got to have at least two, right? You can't do a drug study. So, okay, well, one factor is going to be drug exposure, and so we're going to give people the drug. Well, what else, right? You have to give some other group either more drug or less drug or no drug. There has to be some difference in the amount of drug given. Otherwise, you can't look at differences, right? So minimum number of levels for a factor will always be at least two. Can be as many as you can afford to do beyond that. Most typically, you'll see 2 to 3 levels of a factor, sometimes 4. Going beyond that gets difficult just in terms of the more factors you have, the more ways you're going to divide people within groups, especially in a multifactorial study. And if they're between subjects factors, you're going to need larger and larger sample size, right? Because within each kind of level of factor, you need a certain number of people to have sufficient power to be able to find differences between groups. So most commonly you'll see factors that have 2 levels or 3 levels, sometimes 4. In a factorial design, obviously what makes it factorial and not univariate is that there's more than one factor, right? In a univariate design, a one-way design, people in the study are grouped, they're differed based on differing one way. in a factorial design, they're differing in more than one way, differing on more than one factor, right? So at least two factors to be a factorial design. So we're going to give people different levels of the drug, and we're also going to, that's one way they differ, and then we're also going to let some people eat before we administer the drug, and other people we're going to have them fast before we administer the drug. So now people in the study are differing two ways. They're differing depending on how much drug they're getting, and they're differing on whether or not they're fasting or not before getting the drug administered. Right? And again, you can have multiple factors in a study. It depends on how many people you have to be able to do that. Okay, so as we're thinking about these multiple factors, and each factor has multiple levels, when you have multiple factors being kind of crossed, you end up with different cells. Cells being the total number of conditions in the study. And conditions, what condition you're in, differs depending on which level of each factor a group experiences. Right? So if you have a 3x2 design, right, so that's two factors, right? One factor has 3 levels. The second factor has 2 levels, right? 3x2. Now it's pretty easy to figure out how many conditions you have because you just multiply the numbers. 3 times 2 is 6. There's 6 different conditions. So if we had our drug study, 0 milligrams, 20 milligrams, 30 milligrams, and fasting or not, okay, well your conditions are not fasting with 0, not fasting with 10, not fasting with 20, and then fasting with 0, fasting with 10, fasting with 20. Those 6 different experiences you could have in that study. That's 6 different conditions, so there are 6 cells. Right? If you had a 2x3x2 design, right? So 3 factors. Well, again, how many cells would there be? Just multiply it out. There's 12 different cells, 12 different little mini groups in that study. 12 different ways that people could all be different from each other. And as I said, you can have more than 2 factors. It's at least 2 of them to be a factorial design. When it's 2, you can also call it a 2-way design. Guess what? If there's 3 factors, 3-way design. 4 is 4-way design. On and on ad nauseum. But again, the more factors you have, the larger sample size you're going to need. Because even with just a 4-way design, if all 4 factors only have 2 levels, like the simplest 4-way factorial design you can have, then how many cells do you have? Think about that. So that's 2 times 2 times 2 times 2, right? 4 2s. Well, 2 to the 4th power, that's 16. So 16 different cells, 16 different conditions. That's a lot of people, right? And I think SPSS won't even do the analysis if there's less than 5 people in a cell. And you're recommended to have, closer to 20 in a cell. So with the super lowest number, 5 people times 16, that's an N of 80, right? And that's going to be a super low powered study. If you have 20, 380, all right. Pretty large sample size for such a design. So, and again, even though you can do these kind of 4-way, 5-way, 6-way factorial designs theoretically, most commonly you'll see 2-way and 3-way. At the most, usually you'll see 3 factors. And when you have 3 factors, typically each factor has 2 levels, and one of them might have 3. You don't see much beyond that just because, again, you need really large sample sizes to be able to find group differences with that many levels. Okay, and as we said earlier, each factor can be a between subjects or within subjects factor. So if all the factors in your study, if you have 2 or 3 factors, if every single one of them is between subjects, so that would be a fully between subjects design. So with our drug study, if people got either 0 milligrams, 10 milligrams, or 20, you didn't get 0 once, and then later you got 10, you just got 1 level of that. And then you also only got 1 level of the food variable, either fasting or not fasting. That means that there's some people that, fasted and got 0 milligrams of the drug, and they didn't get any other combination in that study. Right? They only got one level of the drug factor and one level of the food factor. So if that were the case, that would be a fully between subjects design. Right? So if we did that, and we did, again, if we did it as a 3x2, 3 levels of drug, 2 levels of food. If you wanted to have, let's say, kind of middle ground, you said you wanted a minimum of 10 people per cell, and you did a fully between subjects design, how many people would you need? Okay, well, 3x2, that's 6 cells, 10 people per cell, and those are all unique people in this cell different than people in that cell. So that's 10 times 6 is, I need a minimum N of 60. Okay, cool. So what about if it were a fully within subject design? So that means that each factor is fully within. Be challenging in our drug study, but you could do it given enough time, where, so you as a subject, at some point you're going to get 0 milligrams, 10 milligrams, and 20. At some point you're going to be not fasting and fasting in every possible combination. So at some point you're going to be fasting and we give you 0 milligrams, you're going to be fasting and we give you 10, you're going to be fasting and we give you 20, and then later, some other time, you're going to have eaten, we'll give you 0, you're going to have eaten, we'll give you 10, you're going to have eaten, and we'll give you 20. So you receive all levels of both factors. Well, that's fully within subjects. So again, if we wanted 10 scores per cell for this design, but if we did it fully within, how many people would we need? Well, again, it's 3 times 2 is 6 cells. But now, if it's fully within, the people in this cell are the same as people in that cell, because it's you. You had to do both things. So now our total N, number of our sample size, is 10. Right? So obviously, you can see the advantage of doing a fully within subject design. For the same number of scores in a cell, you can get away with a lot fewer people. Right? Of course, you're probably already thinking, yeah, but if I'm getting the drug all these multiple times and fasting multiple times, that's probably going to affect my score on the dependent variable if you're going to measure me 6 different times on whatever this outcome is. Yeah, and you're right. So there are small, obviously, disadvantages to a fully within subject design. And so sometimes you try to find this middle ground where you have, one factor that's, at least one factor in the study that's between, and then at least one other factor that's within. And when you do that, if it's not fully between, fully within, it's a little bit of a mix. Well, I'd say mixed subjects design. Right? So you could do it, and you could do it either way. But let's probably go with the simplest way to talk about it would be if the drug factor were fully between subjects factor, but then the food factor were within subjects. So people are going to get just one level of the drug, either 0, 10, or 20. But they're going to be measured when given the drug after fasting and after eating. So if pick somebody randomly out of my sample, this person's experience, okay, they're in the 20 milligram of the drug group. Okay, I'm going to measure them twice. Once after they've been fasting, and then I give them 20 milligrams. Wait for the drug to clear out of the system, maybe the next day, and then I'm going to give them food. They're going to eat, and again, that person will get 20 milligrams again, right? Because I want to compare their 20 milligram score to their 20 milligram score, with the only difference being did they fast or not fast, right? And do that for every person. So one variable is within subjects, the other variable is between subjects, and that would be a mixed subjects design. Mixed subject design is very common, particularly whenever your within subjects factor is time, right? If you're doing any kind of therapy study with pre-post, and you have people in different groups, okay, this group got CBT, this group got narrative therapy, and we measured their some sort of symptom level before and after therapy. Okay, well, we're going to compare your scores before to your scores after, so that time is a within subjects variable, but you're only going to receive one type of therapy, and that'll be a between subjects variable, making it a mixed subjects design. Okay, some more terminology that will probably make more sense on the next slide. Marginal means. So this is thinking about whenever you have a factorial study, you can calculate the average score on the dependent variable for one level of a particular factor averaged across levels of another factor. Again, thinking in a kind of the simplest 2x2 design here. So if we're looking at or even a 3x2, but it's a two-factor design, thinking about our drug study, you can imagine having this kind of matrix of scores with 0, 10, 20 milligrams, and fasting, not fasting. We said, well, what's let's calculate a marginal mean for people that were not fasting. Okay, so you'll have people for not fasting, you have three different scores, right? The 0 milligram score, the 10 milligram score, and the 20 milligram score. If you average those out to the side, out to the margin, that'll give you a marginal mean. Okay, well, that's the average score on the DV for when people were fasting, regardless of how much drug they got, or averaged across how much drug they got, right? Averaged across one factor, at one level of the other factor, what's the average? And we calculate marginal means to help figure out if there are main effects. So the main effect is whenever there's an effect of one factor averaged across or ignoring the other factor. So I said this is when marginal means are different for a factor, because for a factor that has two levels, you have two marginal means, right? One for each level. And are those two means different? If it's a three-level factor, you'll have three marginal means. Is any one of those means different from any of the other two? If so, you've got a main effect of that factor. So how many main effects are you going to have in a study? Potentially, you'll need to examine main effects for however many factors you have. Right? So if you have a 2x4 design, how many factors do you have? Oh, is it 8? No, it's not 8. That's how many cells you have. That's how many conditions you have. But you have two factors. One was a 2-level factor. One was a 4-level factor. So there's two possible main effects. Right? If you have a 2x2x3, that's 3 main effects. If you have a 2x2x2x2, okay, 4 possible main effects. Right? So there's a possible main effect for every single factor. However many factors you have determines how many possible main effects there are. And again, that's just the effect of one of the factors ignoring all the other ones, where you kind of smush everything together and average across all levels of all other factors. Okay, let's just look at for gender differences. Were men different than women, regardless of everything else you did to them? Okay. Main effects different from simple main effects, sometimes referred to as simple effects. It's a little more complicated maybe. This is the effect of one factor on the dependent variable within a particular level of another factor. Okay. So if we think about our drug study, so within a particular level of food, so there's two levels of food, fasting and not fasting. So let's say within the fasting level, so we ignore the food level for a second. Okay, so within that fasting level, what are the effects of drug within that level? So that's looking at, okay, for fasting, the effects of the drug are the differences between 0, 10, and 20 milligrams. Those differences between those cell means, if there are any there, 0 versus 10, 0 versus 20, 10 versus 20, those would be simple main effects, right? So looking at mean differences between cells, not between marginal means. And you don't go kind of diagonally, you're going within a level of a factor. So for every study, there are potential main effects. There's always at least one potential interaction effect. Interaction is when the effect of one factor on the dependent variable differs depending on the level of another factor. So again, this is why we talk about simple main effects. Interactions happen when the simple main effect of a factor is different depending on the level of the other factor. Right? So let's say in our drug study, you've got within fasting 0, 10, 20 milligrams of drug, and as we increase drug from 0 to 10 to 20, we see the means on the dependent variable going up. right? You're getting higher scores in the DV when you got 10 versus 0, and then higher again when you went from 10 up to 20. Okay, that's happened if you're fasting. Scores are getting higher. So the simple main effects all going in one direction. Now, if we had people that got food before getting the drug, and we see a different pattern, so oh yeah, we found this increase in response on the DV with higher levels of drug when they're fasting, but when they ate, opposite, highest scores were with lowest levels of drug, and as you gave more drug to people that had eaten, scores actually went down. Okay, well then that suggests interaction because the effect of drug was different depending on if they ate or not. Right? So the effect of the drug factor on the dependent variable wasn't consistent. It changed depending on what level of the other factor people experienced or belonged to for a subject variable. Okay, here's an example. Maybe it'll help make it make a little more sense. Example study looking at treatment study. People whose presenting problem was either social phobia or specific phobia, and they received therapy either face-to-face or online. And the dependent variable was symptom severity after treatment. So no pre-post, just a post-treatment study. Fully between subjects design, right? So people couldn't have both social phobia and specific phobia in the study. And they couldn't get therapy both face-to-face and online. It was one or the other. So, fully between subject design, how many factors should we have? We've got presenting problem is a factor, and it's got two levels. The two levels being social phobia, specific phobia. And then we've got a second factor, modality, also with two levels, face-to-face or online. So it's a 2x2 between subject design, fully between subjects. And as I said, our dependent variable is symptom severity after treatment. Okay. So if we want to look at main effects, how many main effects are we going to have? We've got two factors, so two potential main effects. So the main effect of presenting problem. So the main effect of presenting problem, what we're looking at is, okay, scores in the DV, so people's symptom severity after treatment, will there be differences depending on presenting problem? Period. Right? Regardless of what kind of treatment they got. People that had some type of treatment, whatever it is there going to be difference in symptom severity for people who had social phobia versus people that had specific phobia? So to do that, I calculate the marginal means, right? And that's quite simply is figuring out the mean, the average out in the margin. So for social phobia as a presenting problem, you have two scores, right? A score for people that got face-to-face, people that got online. 8 plus 2 is 10. Divide that by the 2, it's 2 scores. Gives you a marginal mean of 5. Specific phobia, 2 and 7. The average is 4.5. So our two marginal means are 5 and 4.5. And we're going to compare those to see if there is a main effect of presenting problem. So the difference is being 0.5. Pretty small difference, right? We don't want running an analysis here, and we don't know how much variability is in those scores. But it's unlikely that that's a significant main effect. Probably no statistically significant difference in between groups in terms of symptom severity after treatment, depending on if you had social phobia or specific phobia. So probably not a main effect there. But we've got one more main effect to look at. That is of modality. And again, same thing. We calculate marginal means. Now instead of going horizontally, we come down vertically. For the modality of face-to-face, 2 scores, 8 and 2, average is 5. Online, 2 and 7, average is 4.5. And again, and it won't always work out like this, but this time we get this similar marginal means, also a difference of 0.5. Probably not a main effect of therapy modality, suggesting that, okay, yeah, overall, there weren't differences in symptom severity depending on what type of, how the therapy got delivered. Right? So if you stopped here, if let's say these were not statistically significant findings, okay, well, there was not a main effect of problem and not a main effect of modality. So people didn't differ on how bad they were doing, based on what the presenting problem was, or on how the therapy was delivered. So if you stop there, well, I guess we didn't find anything. Nothing mattered. But if you look at the numbers, clearly something mattered. Something was going on here. And that's where it's helpful to look at the interaction. Okay, two ways to do it. You can go horizontally or vertically. Both are legitimate, both are fine. Just don't go diagonally or go in circles and weird stuff like that. So you start off talking about, okay, I'm going to pick one variable, one factor to start with. So I'm going to say, let's start with presenting problem. If the presenting problem was social phobia, right? So I'm locking into one level of one factor, and now I'm going to interpret the simple main effects for that level of that factor. So when this is true, when presenting problem is social phobia, what was the effect of modality on symptom severity? And the effect was, okay, well, when people present with social phobia, people were worse off with face-to-face therapy than they were with online therapy, suggesting that, okay, if they had lower symptom severity for online was better when people were presenting with social phobia, right? Okay, so there's a simple main effect. We have this direction, face-to-face, worse scores than online. And then I go down, I drop right down. I started with social phobia, one level of presenting problem. Now I go to the next level of presenting problem. However, when people presented with specific phobia as the presenting problem, I see a different pattern, right? I see that face-to-face scores are lower than online scores, suggesting that, okay, when people present with specific phobia, you have lower symptom severity for face-to-face. So when people presented with social phobia, online therapy was superior to face-to-face therapy. However, when people presented with specific phobia, face-to-face therapy was superior to online. Okay? So we see a different pattern, and it switched. It went opposite. So that's one way, and you could stop there. That you've interpreted the interaction, right? You don't go any further typically. I just want to show you there is another way to interpret it, right? Or, and again, you don't do both of these. You pick one, or you go vertically, right? Because before we said, okay, let's pick one of these presenting problem levels. Now we're going to start at the top and go, okay, let's pick one modality. Okay, so when the therapy was face-to-face, what happened? So we're looking at the simple main effect of presenting problem for one level of modality. Well, when it was face-to-face, severity was worse after treatment for social phobia than specific phobia. It's just that when face-to-face treatment was used, the outcome was better for specific phobia than social phobia. However, when the modality was online, the outcome was better for social phobia than for specific phobia. Again, we see this reversal in a pattern, right? And if these were significant differences, if these summings were significantly different, either way we interpret this, we see a significant interaction. And so for a significant interaction to happen, you need basically a change in the pattern. And the simplest way to know there's a change is when it reverses, right? When you have, okay, greater than going this way, and I move over to the adjacent row, or if I'm going the other way, I move down to the adjacent, move over to the adjacent column, or move down to the adjacent row. If the sign flips, I go from greater than to less than, okay, well, that's an interaction. Or if it goes from greater than to equal to, that's also an action. That's a different pattern. Or if it goes from vastly greater than to just barely greater than, that's also a change in the pattern, right? So for the modality, we have 8 is greater than 2, and online 2 less than 7. Pretend for a minute we have 8 less than 2, and 8 greater than 2 and 7 greater than 5. Okay, that might also be an action, right? Because there's a bigger difference for face-to-face, 8 being different than 2, than for online if it were 7 greater than 5. Okay? So again, anytime the pattern changes when you go across levels of a factor, that suggests the likely presence of a statistically significant interaction. Okay, so when you interpret factorial designs, first you always look at the main effects, right? Was there a main effect of this? Was there a main effect of this? But if the interaction between two factors is significant, it qualifies any significant main effects you have. So, and you can have an interaction without main effects or with main effects. It happens both ways. But if you have a significant interaction, that main effect or main effects are qualified. Whoops, that's where did that show up? There it is. So when there's an interaction, you say, oh, yep, there was a main effect of yada yada of drug, of presenting problem, whatever. But it wasn't always true. It's like, okay, so it could have been, well, we have a main effect of presenting problem. People with social phobia had worse scores after treatment, regardless of treatment. However, that main effect was qualified such that it wasn't always true. When treatment changed from face-to-face to online, we had a different outcome. Excuse me. So for lack of a better word, the interaction trumps the main effect, right? It qualifies it. To interpret factorial designs, you're almost always going to need to conduct post hoc tests. And if you have any of your main effects have factors that have more than 2 levels, you'll need post hoc tests. If you have just a 2-level factor, fasting, not fasting, if there's a main effect of that, what's super easy to interpret, you okay, well, there's only 2 means here. There's a main effect to this, and there's differences. One of them is bigger than the other. You interpret that. But if you have your, like your drug factor with 3 levels, if there's a main effect, there's a main effect of drug, you don't know which of those 3 means are different. All you know is, yep, it's different. Again, you can look at the numbers and go, oh yeah, this one's bigger than that one. But is it bigger enough? Is it statistically significantly different? Well, you don't know until you run post hoc tests, right? So you kind of go in after the fact, post hoc, and you do pairwise comparisons among those means. There's a variety of ways to do that with, Tukey's honestly significant difference, Chaffee test, pairwise comparison with the Bonferroni correction, Fisher's least significant difference, and lots of debates among statisticians about the best way to do it. But generally, you don't want to do too many post hoc tests because you're worried about family-wise error rate, right? Because again, the more tests you do, the more likely it is at some point you're going to make a type 1 error. So you want to be selective about what you're comparing. But you got to do it if you have a factor with more than 2 levels. You also do it for any significant interaction, right? Because the simplest interaction you can have is going to be for a 2x2 design, which means you're going to have 4 cells. If you have 4 cells, that's 4 different means. Which ones differ from each other, right? So you're comparing the cell means, but it's not every possible combination, right? You don't compare them. If you think about that box in the previous page, you don't compare it diagonally. You go across or down. You don't go across the diagonal. You don't need to make those comparisons. Excuse me. And the other thing to keep in mind, again, to help predict against family-wise error rate is you don't run post hoc tests unless the omnibus test is significant. Well, what's the omnibus test? That's the overall, that's the big test you did at first. Typically, an analysis of variance of some sort, right? So if your factorial ANOVA was significant, you had a significant F and you had a significant, not just the overall F, but if we're going to look at all the cell means to interpret interaction, we're only going to do post hoc tests on those cell means if the interaction term is significant, right? Because we'll get an overall F for the ANOVA, which doesn't really mean anything, but we'll also get what we interpret we'll get an F value for the main effect of each factor and an F value for each interaction that exists. Excuse me. Okay, a little look at graphing the results. In this example, looking at when people are driving in their car and the speed they're going, if traffic is sparse or heavy, being one factor, and if the music they're listening to is heavy metal or classical music, how fast are they going? So if we look at the first graph, and you'll see whenever you graph factorial design, it's particularly a two-way one, you'll pick one factor to put along the bottom, right, of different levels. And then the other factor will get put in a key up in the top, right, where you assign, circles and squares, circles and triangles, pluses and minuses, whatever, so that we can see, okay, for this first one, when traffic was sparse, okay, well, when they listened to heavy metal, that's the oval. Okay, so they were going pretty slow, but when we listen to classical, going a bit faster. We look over here, when traffic was heavy metal going slow, classical driving faster. And now if I want to look at the main effect of music type, I look at the average value for music. So the average value for heavy metal is the point on the line halfway between the two ovals. Right. The average value for classical is the point on the line halfway between the two triangles. Right. So think about those points midway on both lines, and if those points are distant from each other, that suggests a main effect. And it looks like there's a main effect here. People were driving faster when listening to classical music than when listening to heavy metal music. Now, for what's the average speed for when traffic was sparse or heavy, right? Looking at that potential main effect, those kind of marginal means. So when traffic is sparse, the average value you got to think is a point it's not on the line, it's a point kind of out here in space above this kind of sparse column that's halfway between the triangle and the oval. A midpoint there. Imagine a dot. Same thing for heavy, between the triangle and the oval in that column. There's a dot. Now, if there's vertical distance between those 2 points, that's just a main effect of that factor. If they're on the same plane, along kind of the, kind of imagine a coordinate plane here, then there's not. And it's like, yep, doesn't seem to matter. The density of traffic didn't have an effect on speed. Right. So that's how you interpret the main effects. And the interactions, easiest thing to interpret, if the two lines cross or look like they're soon going to cross, interaction. If they're parallel, no interaction. In this case, no interaction. It was just, yep, faster with classical, slower with heavy metal. Density didn't really seem to play a role here. Right. Look at the second one, we see a fully crossed interaction, right? Where when traffic was sparse, people were going much faster with classical music than heavy metal, but when traffic was heavy, they were going much faster listening to heavy metal music than classical. Right? Again, you try to figure out the main effects. You got to find those midpoints on the lines, and when things are fully crossed, in the midpoints between the shapes and those kind of vertical columns, it looks like probably not a main effect of either one. And that's when you get that perfect X, typically you're going to have, that means no main effects and just interaction. Or we have this third one, looks like the lines are, soon about to cross. Like it's imminent. They're not like, oh, they're just slightly not parallel. No, look, they will soon touch. So it looks like an interaction. So when traffic was sparse, basically we have very little difference in speed depending on type of music. But when traffic was heavy, here's this big difference in speed. Okay, so that means that the effect of one variable differed depending on the level of the other variable. That sounds like an interaction. And if we look for main effects, okay, traffic was sparse, going pretty slow. Traffic was heavy, midpoint a bit higher. So it seemed to be going overall faster when traffic was heavy. Which you notice that main effect, like, well, yeah, but that's not true for people listening to classical music. They actually went slower in heavy traffic. Yeah, but statistically, you might get that main effect anyway if the speed is fast enough for those heavy metal folks in heavy traffic, which is why we say those main effects are qualified by sync interactions. Like, yeah, there's a main effect, but it's not telling the full story. And if we're looking at the effect of music, overall, people going faster listening to heavy metal than classical, because the midpoint of one line is much higher than the midpoint of the other line. The usefulness of factorial designs, kind of when they come in handy. Excuse me. Pretty helpful for I can rule out alternative explanations, right? And this is sometimes whenever you're hoping that there's not a significant interaction, right? Where you say, okay, I think this variable, my independent variable has an effect on dV. I'm going to throw in this other variable. People say, well, is it always true? Could this other thing be playing a role? And I want my independent variable to have the same effect regardless of, let's say it's gender is this kind of other thing. Well, maybe you're going to find differences because of men and women. But I want to say, nope, look, there's no main effect. There was no difference between men and women. It's just what I did to people caused this difference, and there's even no interaction. Or sometimes it's kind of the opposite. I want, exceptions to some rule, right? Where I'm looking at moderation, right? Different than mediation. Moderation, which is really what all interactions look at. And that's where, okay, yeah, I think this IV has this effect on this dV, or this grouping variable. There's these group differences, but it's not always true. It's not true when this. It's not true. It's true for men, not true for women. Or it's true for older adults, not true for younger adults. And I can look at that with a factorial design if I have a significant interaction. I can also identify kind of essential elements of a thing like an intervention study. Let's say I'm looking at therapist characteristics and outcome of therapy. And I'm looking at, okay, I have therapists of different levels of experience and therapists that also differ in how warm they are, right? So these two different factors. What if there's a main effect of both, but no interaction? Right? So what does that mean? Okay, so more experienced therapists, their patients had better outcomes, and let's say warmer therapists, their patients had better outcomes, but there wasn't a significant interaction. What does that mean? So as we go from less experience to more experience, that the warmth factor is true regardless of experience. So for inexperienced therapists, being warmer is better. For more experienced therapists, being warmer is better. That's what we see if there's not an interaction. Okay, it's just that both those things are essential elements to improving client outcomes. So you can really tease apart a lot more of the pattern of effects with the factorial design. And again, the more factors you have, the more complexity you can explain. But there's a cost in terms of subjects. Okay, take home. As I said, the complexity increases with the number of factors, increases with the number of levels, which good and bad. Because the more complex we have it, the more we can explain, but the harder it is to do, and the harder it can be to interpret as well. Right? Like a two-way interaction, as you've probably already started to figure out, can be a little tricky to interpret. Now think about a three-way interaction, right? Which a three-way interaction saying that, okay, these three different variables, three different factors I looked at, and I've got let's say they're all two levels, a 2 by 2 by 2. If there's a three-way interaction, then let's split. One of the factors is gender, easiest thing to think about. If we're thinking about kind of a binary gender example here, male and female. For males, the interaction between the other two factors looks one way, but for females, the interaction between the other two factors looks different, right? And then you got to go drop down within those. Well, what are those interactions, and what are the main effects? Okay, now think about if it's a 4-factor study and you have a 4-way interaction. It can get really tricky to try to figure out, well, what does that even mean? The majority of studies looking at group differences use factorial designs, right? You don't see very many studies out there that are univariate nature. We're just looking at one variable, and it's not uncommon to manipulate just one variable, but almost always they'll throw in a subject variable. Okay, we're going to do this thing, but we're going to say, okay, is it true? Does this spec hold true for men and women, for older and younger, for people that went to public school versus private school? Usually some other variable, often a subject variable or a demographic variable that they want to know. Did that play a role as well? Last thing, keep in mind too, not all factors are independent variables. We kind of get in this mindset when we talk about factorial designs, when we start thinking about the analyses and ANOVAs. Oh, if I have factors, I've got main effects, it must be an independent variable. Not necessarily. A lot of times factors, again, are subject variables or quasi-experimental variables. Sometimes they're also IVs. Okay, that's all for now. Take care.